In material science, defects in a crystal lattice are called dislocations. In this picture is an example of a dislocation made using a bubble raft, a common visualization tool for observing dislocations. In the picture, we see two rows of bubbles, which represent atoms in a crystal lattice that start out running alongside each other, but are then separated by an additional row of atoms that was inserted in between them. There are two main types of dislocations: edge dislocations, like the pictured dislocation, and screw dislocations. Edge dislocations result from an extra row of atoms being added. They move parallel to an applied stress. Screw dislocations are the result of shear force and move perpendicular to applied stress. Dislocations in a crystal lattice can move in response to stress. The movement of dislocations, as seen in this video, acts in order to reduce strain in the lattice. As one bubble pops, creating a vacancy, the dislocation slides through the lattice to fill in the empty space, reducing surface area. One way to imagine the distortion of a crystal lattice made by a dislocation is the Berger's vector. In a perfect Berger circuit, like the one being drawn, an ordered ring made in the lattice returns to the original atom. The pictured circuit travels right 2 atoms, down 1, left 2, then back up 1 to return to the original atom. In a distorted Berger circuit, like the one being made in the bottom right, distortions cause the circuit to end in a different location than the start. The new circuit travels left 3 atoms, down 3, right 3, and then up 3. However, it doesn't return to the original atom. In order to complete the circuit, an additional line must be drawn, here in gold. The golden line is called the Berger's vector, and marks how the dislocation distorted the lattice. There are two cases that result from movement of dislocations towards each other. The strain field of a dislocation has part tension and part compression, and the interaction of these fields with other dislocations can change how they move. Alike fields repulse each other, while dissimilar fields will attract each other. These fields can cause the dislocations to stack up in a material, repulsed by one field while also being attracted to another field in the same direction.
Grain boundaries. A grain boundary is the interface separating two adjoining crystallographic orientations. Low-angle grain boundaries are those with a misorientation less than 15 degrees, while high-angle grain boundaries are greater than 15 degrees. Dislocation grain boundary interactions. As a dislocation approaches a grain boundary, it moves along the grain boundary, and as it does, it disrupts the orientation of the grains adjoined to the grain boundary, either making the misalignment worse or resolving it. Next is vacancy. A vacancy is where there is a normally occupied lattice site that is empty. This will disrupt the crystal lattice because the surrounding atoms will slightly relax and fill the empty space. Next is interstitials. This is when a lattice site holds an alien atom that is larger or smaller than other atoms in the lattice, which causes tension or compression on the surrounding atoms. There are two types of interstitials: substitutional foreign atoms and interstitial foreign atoms. Here you can see a substitutional foreign atom, which is when the interstitial atom takes the place of an atom from the crystal lattice, while an interstitial foreign atom is in between the lattice sites of. Here you can see the grain boundaries react as a stress is applied to the system. The grains move and the grain boundaries shift and even align with other grain orientations to relieve stress. You can also see grain boundaries shift as dislocations move through them. And you can see the individual atoms enter tension or compression as the stress is being applied.